conventional microscopy, or even in traditional imaging in general, the real optical signal cannot be easily distinguished from background light or detector noise. Our implementation uses a quantum light source that emits entangled photon pairs that are spatially correlated, and one of these photons illuminates the object while its partner acts as a reference, and we utilize these quantum correlations to enhance our imaging relative to the classical case. And we perform this using an array detector, in this case an EMCCD from Andor, and this improves the efficiency compared to historical methods in which scanning detectors were used. So our solution is as per the setup at the top. So the two photons are spatially separated in the far field. One interacts with the object, one has a free optical path. This plane is re-imaged onto the EMCCD camera, and on the camera we detect two regions, the probe beam and the reference beam, two separate regions. We take these two regions, flip one around, and then perform an AND operation, which serves to preferentially select the events that correspond to real photon pairs and to preferentially reject the events that are uncorrelated, so those which correspond to noise, external noise or detector noise. So here we have a more easy to read diagram which I'll describe the technology. So we use a BBO crystal cut for type 2 down conversion, so the two photons are spatially separated. We detect the reference beam on the camera as a beam, whereas the probe beam passes through the object, in this case a bird, and is imaged onto a different portion of the camera sensor. And we also illuminate a thermal mask using a mask using a thermal light source, and we overlay this on top of the region of the sensor that detects the probe beam. So in our case we have the quantum bird imprisoned within a classical cage, but by performing the AND operation as described in the previous slide, we're able to release the bird from its cage. And you can see here we can do this for a range of light levels in which the cage is up to 10 times brighter than the quantum illumination of the bird. So you see here, you can see the bird in the cage, but as you increase the cage brightness, you're not even able to ascertain the presence of the bird. But after performing our analysis, you can release the bird from the cage. And here we are currently limited by detector noise and the data rate of our detector. So target and uses of this technology. So of the setup itself, we're in discussion with a number of manufacturers to enable their camera technologies to be evaluated, and also longer term the application of such a imaging scheme is in the field of quantum LiDAR, where we're able to reject a spoof background such that you are able to distinguish your red balloons from your MIGs masquerading as such. And here on the right we also have a microscopy implementation, for example, where we have a wasp wing which you cannot tell what it is in the classical image nor in the originally recovered quantum image, but through performing some processing we are able to recover an image of the wing.